In section 3 of chapter 1 in our textbook, we look at equation solving. Our textbook starts off very basic as far as equation solving is concerned. And I know we already have a lot of experience in earlier courses with basic equation solving, so I'm going to focus on some more specific, more involved equations. So you can look at our first objective here. Notice we are going to be solving equations involving fractions and decimals today. Okay, and then from there we're going to move on to solving multivariable equations. It's an equation that has several variables to it. You're asked to solve for one of the variables. Let's get right into an example here. I'd like to solve this equation for n and check the solution. Now understand what an equation is first of all. It's basically where you're taking two expressions and you're setting them equal to each other. You're trying to figure out what value for the variable makes the two equivalent. Okay? Now I think we can all agree that decimals are not our favorite to work with. We would prefer an equation to not have decimals in it. Well, I can take this particular one that has 4 decimals to it, and I can manipulate it so that those decimals clear. Okay. To do so, I'm paying attention to the fact that the decimals in this equation, they go as far as the hundredths place. Okay. So if I were to take both sides of the equation and multiply them by 100, I will get those decimals to clear. Think of this as like you're using your distributive property. So 100 times 0.43n, that's going to move that decimal place 2 spots to the right, and we're going to end up with 43n. 100 times 0.1 will also move your decimal place 2 spots to the right, and you'll end up with 10. Or on the right side here, distribute the 100. 0.7, that's 7/10 times 100 will give you 70. And then negative 0.17n times 100, or 17 hundredths times 100 is going to give you minus 17n. Once we're here, I think everybody's going to be a lot more comfortable with how to proceed. I'm going to move my variables to one side now. So I'll add 17n to both sides. And then at the same time, I'm going to move my constants away from the variables. So that's going to result in 43n plus 17n would be 60n. And then 70 minus 10 would also be 60. And then we can divide both sides by 60. And now we wind up with n equaling 1. So quite a complex equation to result in a solution of 1. How about fractions? Oh, let's back up here. Sorry. I probably should have checked my answer, right? Checking an equation is simply just taking your solution, plugging it back in for the variable. So if I put 1 back in for 0.43 times n, that's going to give me 0.43. Add that with 0.1, I'll end up with 0.53 on the left. And then if I put 1 in for n on the right side of the equation, I'd end up with 0.7 minus 0.17, which is also going to be 0.53. So checks out. All right, solve and check the solution here. Notice there are several fractions in this particular equation. I know we don't like working with fractions, So we can use a pretty similar approach to what we did in the last example in order to clear the fractions of this equation, make it a lot more user-friendly. Okay, now first of all, I'm going to rewrite this so that I get rid of those parentheses. This is 2/5 x plus 3/7 equals 1 minus 4/7 x. Okay, and here a power of 10 isn't going to cut it. Instead, to clear those fractions, we're going to have to multiply both sides of the equation by a common denominator. And preferably you want the least common denominator. So out of all the fractions in the equation, we've got 5 and 7 as our denominators. The least common denominator would be 35. So I'm going to take this side and multiply it. I like to think of it as 35 over 1. And I'll do the same thing on the right side. Okay. All right, once again, utilize your distributive property here. All right, now 35 over 1 times 2/5 x. You can get the 5 to reduce away, and the 35 would turn into a 7. Then 7 times 2x is going to give you 14x. 35 over 1 times 3/7. You'll get the 7 reduce to a 1, and the 35 will become a 5. 5 times 3 will give you plus 15. All right. Now over on the right side, a lot of times I'll see students, they won't multiply the 1 by 35 since the 1 isn't presented as a fraction. But you have to do the multiplication to both terms. Both terms need multiplied by that common denominator. So I'm going to end up with a 35 and then minus 4/7 x times 35. The 7 will reduce, making the 35 turn into a 5. 5 times 4x would give me 20x. Much less complicated equation now to work with. So let's move variables to one side again, constants to the other. So I have 34x is equal to 20. I'm going to divide by 34. And let's reduce here. So 20 divided by 34, they have a 2 in common. That's going to become 10/17. Perfectly acceptable final answer. All right, in the next sheet, you've got 2 equations to try on your own. I want you to pause the video for a few minutes, work through them, and then you can start the video back up and check your work. For this particular equation on the left, notice that all of the decimals are to the tenths place. So I can get away with just multiplying by 10 on both sides. That's going to take me to 29m plus 17 equals 35 plus 23m. Okay, variables to one side, constants to the other. And let's see, 29m minus 23m would be 6m. 35 minus 17, that's 18. Divide both sides by 6. M equals 3. Okay. Let me rewrite this next one here. 3y minus 4/5 is equal to 1/3 y. The common denominator between all fractions here is 15. So I'm going to multiply this side by 15 over 1. And I'm going to multiply this side by 15 over 1. That's going to take me to 45y. Right? Even though 3y is not written as a fraction, it still needs multiplied by that common denominator. Minus 15 over 1 times 4/5 is going to give you 12. On the right-hand side, 1/3 y times 15, that's going to give you 5y. Okay. All right, so I personally like my variables to go to the left, my constants to go to the right, so I'm going to end up with 40y equals 12 here. Divide both sides by the 12, or by the 40, and let's see, they have a 4 in common, right? So 12 divided by 4 be 3, 40 divided by 4, 10, 3/10. All right, moving forward. So in this particular example, we are given a formula. This is the formula for the area of a trapezoid. We want to think of this is a multivariable equation. Okay. A represents the area of the trapezoid. Base 1 and base 2 are the lengths of the bases. I'm sorry, B1 and B2 are the lengths of the bases, and H is the height of the trapezoid. We would like to solve the formula for H. Let's pause and think about why that would be useful. Perhaps you know a set area that you are trying to accomplish in a given scenario. You're planting a garden that you want the size, the shape of a trapezoid, and you know you want the area to be a certain value, but you don't know the proper dimensions to work with. So to achieve that area. So taking the formula and solving it, in this case for H, can help us in identifying exactly what dimensions we need, right? So let's write it out. And there's a couple approaches you can take to this, but ultimately I'm trying to get H alone, right? So somehow I need to be able to account for the fact that H is being multiplied by 1/2, and it's also being multiplied by the sum of base 1 and base 2. I personally like to clear fractions first. So I can multiply both sides by 2, and that's immediately going to wipe out the 1/2 there. Two a is now equal to H times the sum of the two bases. And notice that sum of the two bases, it's multiplying H. So I could divide it out on both sides as one whole piece. I don't have to account for base 1 and base 2 separately. Those will reduce away. And now I can say that for any trapezoid, the height is equal to twice its area divided by the sum of the two base lengths. Okay. All right, moving forward, we got a word problem here for you, just to get us in thinking of setting up an equation to represent a given scenario and then being able to solve that equation. So Carl here, he wants to replace 5 windows in his home. His neighbor Will is a carpenter, and he's agreed to help install them for $250. If Carl's budgeted $1,000 for the total cost, What's the maximum amount he can spend on each window? Define a variable, write and solve an equation. So I think this first directive is crucial for any word problem. Defining a variable. If you don't know what your variable represents, it's going to be really hard to then be able to write an equation for you to solve the problem, right? Defining a variable is as simple as identifying within the problem what you are being asked to find. Okay? Typically, it's where the question is in the problem. So notice it says, what is the maximum amount he can spend on each window? So I'm going to define, I'll just use x as my variable. I'm going to define that to be the maximum amount, maximum dollar amount for each window. Okay. From there, we can set up an equation for this scenario. So looks like there are two factors affecting his total cost, right? We know he wants to spend $1,000, and that $1,000 has to go towards two things: the material cost, so the windows, as well as the labor cost. Okay, the labor cost is a fixed amount. It's a constant amount of $250 to his carpenter friend. And we just need to add that to the cost of the windows, right? Well, there are 5 windows being put in the home, and X represents the cost of one window, so 5X represents the cost of all of the windows combined, right? If we add that to the 250, it can't go over, it has to equal $1,000. All right, now solve this for x. Just subtract the 250 over. And then you'll divide out the 5 there. 750 divided by 5 gives you 150. Right? Now that's $150 can be spent on each window. Write a sentence for your answer.